Thank you to each and every one of you for being here with us today. I, Rudra, along with my co host Reet, welcome you all to this event. Our moderators for today's event will be Sana Bhatia from Shiv Nadar School, Gurgaon, and Achal Vinod from Shiv Nadar University.
Today, this is our second event of cross campus team collaboration after the great success of Energy Boot Camp, where we, as a family of Shiv Nadar Foundation, are proudly hosting this amazing interactive session today in online mode with all of you.
All the members of Shiv Nadar schools, Vidyagyan schools, and Shiv Nadar University have come together to form an association called Nucleus due to a mutual passion for science. Our passions help us all to unite, and the energy we create is what allows us to achieve our individual as well as our group goals.
Before we get started, we would like to express our sincere appreciation to all the members of our nucleus family, which includes the members of Shiv Nadar School, Shiv Nadar University, and the Vidyagyan schools, who generously helped us make this event come together to become a success. We couldn't have done this without you.
I would also like to extend my thanks to the team of IYNS for their constant support to put up this interesting event. Now I would request Reet to introduce today's event and the speakers to everyone present in the session.
Our first topic for today's discussion is Indian Regional Navigation Satellite System, NavIC. This is an independent Indian satellite-based positioning system on critical national applications. The main objective is to provide reliable positioning, navigation, and timing services over India and its neighborhood to provide fairly good accuracy to the user. Dr. Nitendra will take us through the journey of NavIC. Dr. Nitendra, an eminent nuclear scientist working at Institute for Radiation Protection and Nuclear Safety in France, and he is also the founder and president of IYNS.
The second topic for today's discussion is measurements in daily life. In our daily lives, we are closely related with measurements. For example, during a medical checkup, a sports competition, when building a house, when controlling temperature in appliances, or while cooking. As a significant part of measurements are done in laboratories. They need to be able to measure correctly and provide reliable results independent of national borders. In today's session, Dr. Ojha will be discussing the importance of measurements in our daily lives. Dr. V N Ojha superannuated as the chief most scientist of CSIR National Physical Laboratory. He was ex-head of Time and Frequency and Electrical and Electronics Meteorology Division, ex-head of Environmental and Biomedical Meteorology Division, ex-head of Apex Level Standards and Industrial Meteorology Division, and ex-professor in ACSIR.
I request Neelu ma'am, head of middle years of SMS Noida, to share her thoughts on the wonderful event.
Thank you, Keith. Indeed, it's wonderful to always come together from across campuses and also to have such eminent personalities with us to share their perspectives with us and to learn from. This is totally in keeping with the concept based pedagogy that we have, and also to the connected learning platform that we are all going through these days, which is so important in every way. So, to hear it from the scientists themselves and for them to answer the various questions rather than looking them up from the net or textbooks is a different game altogether. And I'm sure children are really looking forward to the two of you answering their questions. And without further ado, we will just hand it over to you both.
Thank you very much, ma'am. I'm sure that everyone here is waiting for today's discussion eagerly, and we will be discussing the two most recent and most discussed topics of recent times.
Now, I'd like to invite Sana Bhatia from Shiv Nadar School, Gurgaon, to discuss with Dr. Nitendra about the new Indian technology, NavIC.
Good afternoon, sir. I'm pleased to be one of the student moderators. My first question to you is, what is NavIC and how does it function?
A very good afternoon to all of you first. And as I mentioned that I'll be bringing some Christmas goodies. So I'll begin with NavIC. A very well posed question. What is NavIC? Firstly, as you know, NavIC is in Hindi, it means the sailor. So sailor, which means like the person who sails out in the sea, and that's how it is. So NavIC is basically acronym for navigation with Indian constellation. So NavIC that way. And it is basically a commercial name, but the technical name is more of IRNSS, which means like Indian Regional Navigation Satellite System. And what it is basically a positioning system. I will not say global positioning system. I'll tell you why. So it's a positioning system, and which you can use in various applications, and navigation is one. So basically, how it functions, it utilizes the geosynchronous satellites, which are, when we talk about geosynchronous satellite, which means so satellites which surrounds the Earth, or circle or have a motion around the Earth for gathering data and stuff. So geosynchronous satellites are synced with the or motion of the Earth. So in a way, they are looking always on a one particular area of the Earth. So it seems like they are
I guess we have lost connection with Nitendra sir. Samik sir, can you just coordinate over a call?
I'm sure we are missing out on so many interesting things that Dr. Nitendra is sharing with us. Can you hear us, Dr. Nitendra? I think. Yeah, okay. I think we will start posing our questions to Ojha now. Read them, or Sana, whoever is the moderator, can take on, please.
Achal, I think you're on.
Am I audible now, ma'am?
Yes,
Okay.
you are.
So,
Yes.
first of all, I would like to thank everyone for giving me this opportunity to be a moderator for this event. So, moving on to the questions. So, sir, we had a couple of questions, but like one of the major questions I would like to start with was why is there a need of defining ampere as a fundamental unit in terms of SI units and not coulomb, which is used for charge? That was one question. If you could shed some light upon that.
Good afternoon, all my young friends. It is indeed a great pleasure for me to interact with you all. The question what you have raised is a very good question, but before that, why not we should have some glimpse of brushing knowledge that why all this system SI unit has started. Okay.
Sure, sir. Sure, sir.
because this is very important to understand the little history of that SI units. This SI unit was basically given the name to the new metric system. Okay. And all this started basically as a 1875, May 1875. There was an intergovernmental organization. This is called CGPM, which has about 62 state members. A state member means various countries who are representing them. And their main aim was to have a harmonization in the system, measurement system. Okay. This harmonization is very important from both trade point of view, from scientific point of view, from legal point of view. And from these aspects, slowly, different units were defined. I'll come to the ampere, why was this there, but first one should understand how this all this system started up. So based on this CGPM, which has the interstate government, means inter-countries which are involved. So from India, also our president has signed that at that time. And now it can be represented by, say, director of NPL or some other institute. They can attend that meeting. This meeting takes every 4 years. So this organization is accepted internationally for the SI units, that is International System of Units. So they basically started, and then they defined that, okay, there should be 7 base parameters. Okay. So these 7 base parameters, there are 6 base parameters which are more related to your, say, physical system, whereas this ampere, what you are talking of, is related as one electrical system. So as a different consequences with due course of time, right from 1875 onwards, people started realizing this system. So in various laboratory measurements were done. Okay, so it was accepted at that time that the current is the system which you can measure directly. Okay, that was you can measure the charge per unit time and you can measure it. So that becomes a sort of a history for that, and it slowly came down. So today also it was accepted in the revised SI unit also. Now you know that SI unit has been revised also now. Now it is not based on the artifacts. So there are 7 base unit which has been revised based unit, and they have been implemented worldwide on May 20th, 2019. So everybody is now accepting that. So that is the reason, one of the reasons that it was accepted by CGPM, and they had been carried forward in the similar way. And it's a simple in measurement, so you can do it, and that's why. But still, interesting point is there. Even in defining this ampere, they have kept the physical constant as a charge, the coulomb. 1.6 into 10 raised to power minus 19 coulomb, they have still kept that value. Okay, so this can give an understanding that why this is so.
Sure, sir. Okay. So the next question that we had was, why is there a need now to redefine these SI units and move over to the Planck system of units that's going to come into play?
This redefinition was very important in the sense. Now, if you again go a little bit to the background, which I think most of the students must have read in science classes also, in physics classes or in science classes, what happened that once we defined 7 base units, so at that time, what was available, the best measurement? So the best measurement was available in terms of, say, meter. We defined 7 base unit as one of the meter quantity. Yes, so this meter was kept as an alloy of platinum iridium, as an alloy. It was kept in the BIPM. So BIPM is again an organization which is internationally funded by all the countries. Most of the countries, they fund it, and this lab is settled, is in France. So that is in the Paris. It is situated in the Paris. And they basically govern in the sense that they help the people all over the world to set up these measurement facilities. So meter was there in terms of an artifact. We call it artifact because it is a scale. Okay. Similarly, kilogram was again a cylinder. I think all this has been studied. So these are artifacts. So what happened with the artifacts? Due course of time, they degrade. They lose weight, like kilogram. It was losing its weight, say even in microgram. But this losing of the weight created the problem in the sense that's not stable, one thing. So even any parameter which is measured in terms of mass, say force, the force is measured at m into a, acceleration due to and m is a mass. So mass is there, acceleration is again there, meter per second square. So if there is a change in the mass, then there will be change in the force Newton also. Okay, so this will not be stable. So the unit of force is a Newton, so it will again change. So these changes in due course of time has to be added or subtracted depending upon how the mass is varying from country to country. And also this BIPM kilogram, which is also called as grade K or big K, lag grade, they call it lag grade. So it is an international photograph of kilogram which was kept in the Paris. Okay, that is a real standard up till now before this new system came. And this was kept in the triple vault. It was locked system precisely, nobody can touch it. With due permission only things were used. And this was used to calibrate the prototype of each country. Like India also has a kilogram, which is called copy number 57. Okay, so this was to be calibrated against that system. So after a few years, it has to go there. They will calibrate it, and again it comes back, and then this calibration is used in the country. So Indian traceability of kilogram, that is dissemination. If you want to measure, say, if you go to the grocery and he put up the kilogram, so that kilogram is traceable or calibrated to NPL, traceable system. Okay, so this type of prototype, with due course of time, they were degrading. So exact values were not covered. They were not stable. So the only thing which was stable was if you redefine in terms of a fundamental constants. If the fundamental constant like h, Planck's constant, it is a very fixed quantity. Okay, so now this fundamental constant, Planck constant, is 6.626 into 10 raised to minus 23 joules and so on. So you can fix it up. So this has to be now calibrated against that fundamental constant. So to realize h, we use watt balance. Okay, to realize this, maybe after some time I can show you the photograph also. But today, just now, I'll just talk to you about the value, what you say. So this was there for the meter. So meter was changed into velocity of light c. Kilogram now changed into Planck's constant h. Similarly, for temperature measurement, this was basically based on triple point of water. So now that has been changed into Boltzmann constant. Right. Okay. The mole was based on the C12 carbon. So now it has been changed into your Avogadro number. So you now see all these redefinitions has resulted into relation with the fundamental constant. So now you appreciate. So now if fundamental constant are stable, they are invariant, they are not dependent on place, time, and this. So it means you can use it very precisely, and all your measurement related to this will be really a perfect measurement because these constants have no uncertainty. Right. Okay. So now you understand that why this redefinition is very, very important, and this will help us in development of the science and technology also, and day-to-day life also it will be useful.
Right. So that was a really great reply. So because like you also answered the next question, which was I was about to ask, like, you know, what is the need to define these SI units in terms of fundamental constants. So now we know that like there was a
because they're all interrelated. They are interrelated. In totality, to understand, if you understand, you have to understand how the things progressed, and now why we define it and what is the importance.
Right.
If the importance is not there, then there's no need of redefinitions.
Definitely. Okay, so moving on to the next question, sir. So this question is mostly, I think, I don't know, it has at least bothered me for a quite long time. And the question is like candela, represented by CD, is used to denote the light intensity in SI units. But in Planck units, we don't have any reference to it. So like, could you shed some light upon this?
Okay. I am sure you all must be from some college level or what?
Right, sir. Yeah, I'm.
Yes, because the question what you have asked is a very good question, but I think the school students may not be able to grasp that or understand to that level. But I'll try to make it as simple as possible.
Sure, sir.
Now, what happened if you are talking, say, in international system of units in day-to-day life activity in general, then these are 7 base units what I have talked about. Okay. So they have their own dimensions, they have their own units. So that is well known. So it will not go into detail. But in the area of particle physics or cosmology, if we talk, then people have started talking in terms of why not have some units, because to realize or unify the theory of, say, relativity at one level and also at quantum mechanics at another level, how to unify that. So now they have given the new name of gravity, quantum gravity. This is just a nomenclature. It is not a real name now. So now in quantum gravity, they thought that suppose if we have to make a units, now these units directly with SI units may not be easy to handle. So they tried to develop these units in terms of known as a Planck units. Okay. Let us define Planck units. Now Planck units means if you talk in terms of gravitational constant, or say reduced Planck, that is h cross, h by 2 pi, or c. So based on this, if you can make a relation and define Planck's units, say Planck time, you can define Planck length, you can define Planck's mass, so on. Okay. So similarly, people thought, why not we define all this like 7 base unit in SI? We should also have a 7 base unit in the Planck units. This is the exact question you are interested in. Right. Because there comes candela in SI unit, but not here. Okay. So now one should understand it is easy to define Planck length, Planck time, and all those things. I'll not go into those details. But the question of candela is that if you see candela is not an easy, it's a very tricky business. In the sense, the definition of candela in SI unit itself is basically a directional system, and also for your eye estimation basically is based on your eye system. So it is in a smaller range, it is there. It's not a very big, okay, right. It's not universal. So this thing cannot work directly in that Planck's candela. So what they did, that why not define candela in terms of just energy itself? So why you put a candela? You can neglect candela because it is very precise only. It's very for limited area. So we should take energy. We can define wherever candela type of things are coming, say luminous flux is coming or intensity is coming, we can define in terms of energy. Similarly, your temperature is also the same thing. You can define again in terms of say power, some energy and all those things. So this is how it's not necessary that all the 7 base units there. Like now charge, again, charge may not be so easy to define in Planck's terminology. So but you know that charge is basically you can define in terms of power and all those things. Right. So that's why what question you have asked, maybe I think my young students or young colleagues or friends may not be able to understand at this level, but this is there. So still a lot of work are going on and people are working on it.
Right. So moving on to the next one, sir. So basically, if you could shed some light upon how are we exactly using these fundamental constants that we just mentioned. So the Planck's constant, the gravitational constant, the speed of light, which is usually denoted by c, and a few more. So how are you using these constants to define units like kg? So if you could explain.
Okay, sure. Maybe if I can share, let me see if I can share. Okay, I can share my slides here. Yeah, okay. Now, maybe I can little bit, again, talk little bit and then come to that. It will be easy for the people to understand.
Definitely. Okay.
Yeah, now we can see that metrology, what we are talking in measurement, is a science of measurements and its application. Is it visible? The slides are visible?
Yes, sir.
Okay. So now these are, again, I have already talked, this can be legal, industrial or scientific, right? So scientific, we are already working. Industry means a good quality product we talk of. Legal means if there are certain issues, like if the nanoparticle goes into your body. So due to that, some problems may start, the biological problem may start. So the legal issues may come up. So you have to define what is nano. It is 10⁻⁹ or not. Okay. So these type of legal issues can be there. Or maybe people are working in the factory and they are hazardous to say asbestos. So how much asbestos has gone? Again, that measurement part will come into picture. What was its toxicity and all those things. So that comes under legal. So in India, we have a weight legal department, the metrology legal department, weights and measure we call it. They work on that, right? Or suppose in the petrol pump, if there is a measurement of petrol, which is to be say 10 liter and he's giving some 9.9 liter, he's making money out of it, cheating. So that again, legal action can be taken against those people. Okay. Similarly, when you go to the purchasing of fruits or vegetable, your weights are used. Those weights are basically governed by weights and measurement department. Legally, they have to be exactly 1 kg. So they are monitored accordingly. So legal is there. So you see that measurement is used in day-to-day life everywhere. Okay, so this is what one aspect one should understand. Now, if you can come down, so you can see definitions. I'll not go into the definition. You can look into the books and all those things. Okay, you can see all those definitions. So this is the system which has now been accepted. Now your question was pertaining here. Okay, so these are now fundamental constants. Okay, physical constant. Now you talked of the H, how this H is used, how it is used to give the value of kilogram. Basically, based on this H, you can define the kilogram, because kilogram up till was artifact. Okay, so this is defined or realized. We call in scientific terms realization. Okay, so in this realization, what we do, we make use of some scientific concepts like mechanical energy is equal to your electrical energy. I think this is okay because energy is conserved. So your mechanical energy is equal to electrical energy. Based on this fundamental concept, NPL, this is National Physical Laboratory UK. Like India, we have a National Physical Laboratory India. We also have National Physical Laboratory UK. There was a great scientist. He is no more now. His name was Dr. Keeble. Okay, so in his honor, we have changed the name of Watt balance to the Keeble balance. Okay, now all over the world we call it Keeble balance. So he was the first person to assign that how to use this wattage, that is your physical, mechanical energy, or then this is your electrical energy. You combine together, power you can combine, and then you can understand that, okay, you can relate these two. They are conservative is there. So he gave the concept of watt balance, and from there he calculated that you can calculate H, and this H can be related to the mass. And that's why this is based on the fundamental. So it has been now accepted worldwide. So after 143 years, your artifact kilogram is now replaced with this Keeble balance. Okay, one realization based on the H. Okay, so this is the system you can see now.
Yes, sir.
This is the Keeble, the watt balance. Okay, this is just a very simple diagram here. So this was done by Keeble in 1975. He gave this idea, and this is now accepted world over. So there are two ways of doing it. Okay, you can just make a weighing static, that is steady state measurements. So what you do, you have a mass and a coil here. This is a coil here. This is a mass here, suspended from a balance. Okay, and then magnetic field there is going down. The gravitational force pulls this up, and this is related to your mg. So mass into acceleration due to gravity is mg, and this side it is balanced by this here current which is passing through the coil, current, the length of the coil, the wire length, and b the gravitational field. So you can balance this. So this is static, you just balance it. Okay. Now another experiment for the same you do is a dynamic measurement. Okay. So in this dynamic measurement, what you do, you put the coil in a vertical speed of a velocity v, so that you have a current voltage which is induced here. Current is passing in the coil. U, that is voltage, is induced in here. You can measure U and I, and based on this measurement of U and I, you can relate your m, g, and v velocity. Right? Now here U and I, that is voltage, is measured precisely by Josephson voltage standard. This Josephson got a Nobel Prize for giving the idea of Josephson effect in 1973. Okay, he gave this idea. So he was working at that time. He was doing his PhD work, and he got that Nobel Prize also. So he was, and then you measure this I through resistance. V is equal to IR. Ohm's law is there. You understand that? Maybe our young people may not have read that. But anyway, what I mean to say, making any fundamental measurement precise, it means everything has to be very precise. So here voltage is measurement by not by a voltmeter. It is measured by Josephson voltage standard, which is very, very precise. Okay, this can measure with a part 1 into 10 raised to power 9. You can measure up to that level. You can measure. Similarly, ohm is also measured. Okay, which is based on the Klitzing constant. Again, he got a Nobel Prize for giving that concept. This is quantum Hall effect, we call it. So based on these two measurements, You put these values here, and these two measurements are again fundamental measurement because they relate with the Planck's constant. Planck's constant and electric charge, they are based on that. So based on that, if this is equated, so this whole equation is now related with H and M. And this is how your H is used here. If you put a fixed value, you can get the value of mass. So now instead of mass as a prototype, as a cylinder, now it is based on this measurements. Okay. The advantage of these type of measurement is that in kilogram, if it is kept in the Paris, you have to send your kilogram there and measure, and this is also not stable. But these measurements you can set up in your own lab. This is the advantage now. So each country is trying to set up this measurement system. NIST America has one system, NPL UK has system, Canada has system. In NPL India also, during I was there, we have tried to set up. So, but it will take its own time. Precision takes its time. It takes about 8 to 10 years to set up such facilities, high precise facilities. And we have set up for 1 gram, and people, my colleagues who are there, they are now working for 1 kilogram. So now you understand that how this is there. Similarly, your velocity of light is again measured by iodine stabilized helium ionizer. We use it and this. Similarly, your time is based on cesium atomic clock. Right. So maybe you can see here. This is your cesium atomic clocks here.
This was one of the major points of high mapping all across the world.
So okay, at that time we can talk, no problem.
Great.
Okay, so we can take, yeah, no problem. I can show you some more things there. Yeah.
Yeah. Okay.
Yeah.
So, okay, moving on to the next one. So basically, I get that, yeah, we have our young participants over here. So it might be a difficult term, but as sir already pointed out, we are, sort of all of the physics is sort of dealing with this whole problem of quantum gravity. So let me take the liberty to, just try to simplify that to our audience as well. So basically, if you see fundamental physics, it's been, it's trying to, come up with a theory, and we have all these candidates as well, like string theory or all these good names that we have. We usually come across in our documentaries. So we already have theories that are coming up to try to explain phenomena which are valid over every length scale. So basically, phenomena of gravitation that are taking place in the heavens, in space, whereas the phenomena that are taking place in the quantum realm. So with atoms or electrons or even smaller particles that we are yet to learn about in our higher classes. So, and there is constantly a roadblock in between that, because we are not able to justify some phenomena just using classical mechanics, which is the theory of the classical world, you can put it that way, or quantum mechanics, that is the theory of the quantum world. So, sir, my next question was intended towards like, if we are taking these Planck units as a basic definition instead of SI units now, so does it point towards some bold assumptions in the field of quantum gravity?
Again, I think it's a good question, but maybe young people will not appreciate or understand that. Because the question is that even in theory, what you have talked of string and other theories, they still are not able to completely define. Okay, so people are still working on that. Now, day-to-day life is basically a different approach than your Planck's units. Okay, so the Planck's units you are using, they are using in a different terminology, in the sense that you are talking where, suppose if you are talking of, say, time of the order of 10 raised to or minus 44, if I say, but in day-to-day life, we are talking time in seconds and milliseconds and all those things. Okay, and even here, if we want to use cesium atomic clock or other, we can measure to 1 part into 16. The best which is available is 1 part to the 19 as a, say, system for measurement of the clock in the whole world. So how you can compete that with what your requirement in the Planck's units? So I think practically that may not be possible, right, to bring it to day-to-day also, one thing. Second thing, whenever there's an advancement as in the technology we go, right now our technology is not able to compete to that level, so that we can measure 10 raised to or minus 44 in time. say Planck time, or we cannot measure say length, Planck length in the order of say 10 raised to minus 35 and so on. So these things we cannot right now do it. But future we don't know, because nobody was expecting that the foot of a ruler, and now we have come to the physical constant. So we are making it more precise and updating our system. So maybe in due course of time it may be possible, but at present scenario this cannot be utilized right now. So we are there with the SI units. We are well to do. People are doing in other way around that. Okay, try to understand Planck's unit also in terms of SI units. That is what the best. In a general way I'm talking. If I have to go more rigorously, it will be difficult. Sure, it's a more general way so people can understand or appreciate.
Right, sir. So, okay, so I think we have already covered, like, even our next question was based on the technology, whether we have the equipped technology, because day in and day out, we are constantly having new technologies in terms of 2G, then we had 3G, 4G, and now 5G is there. So I think there is a law also, I think, like there's this Moore's law, right, which allows us, we have, I think, reached a limit to which we can build the smallest possible transistors, like microprocessors which are used in our laptops or mobiles. So I think that's also is a challenge, right, sir? Like, if
the point what we'll be talking here is more in a different way, to look in a different way. These are called basically technology driven concepts. Okay, so day by day technology will be improving. Need not we follow all the time Moore's law. Maybe Moore's law may be modified or some new law may become, because we don't know how the technology will change. Earlier we used to have a say macro engineering. Now it has gone down to the nano engineering, using lithography and other aspects, or say 3D printers. We have come down to nano level, -9 level. So even in these things, what is important is that are these measurements accurate or not? Now, if these measurements have to be accurate, they are to be traceable to the SI unit.
Right.
So yeah, 2G, 3G, 4G you're talking, or 5G you're talking. Here also the uncertainty in time stamping, time synchronization will become very, very important. And if it goes down, say below 50 nanosecond or 40 nanosecond, then how precisely you can measure that? That again becomes a big question. So what I want to emphasize here, that day by day things will improve in science and technology, but also it's a challenge that we have to improve the newer measurement concepts also. Right. Because earlier we were talking of say meter, micrometer, but now we talk of nanometer, and say we go down, so or picometer, and then so on. We are going down and down. So there is challenge how to measure those things accurately. Right. Okay. So it's technology at one aspect, also your measurement has to be at par to that measurement. So there's a real challenge all over the world. So here basically in these type of measurements, when you go down in measurement or you take cosmological measurement, this fundamental constants will give a correct concept, because you can using the value, a numerical value there. You're not using any artifact value. Right. So that makes the sense there. So this is how these SI units are going to further develop the technology and science and our understanding.
Right. So it was really great to have you, sir. Like, we already have a lot, we have discussed a lot about it. And as you said, I myself also wasn't aware of the fact that like these are, we call them artifacts in like a proper scientific term. So that was really a great thing to know about. So, and I think there are like a couple of more things, like we can just go on for the topic, but I think we also have a time constraint.
Yeah, maybe time constraint, but at least I can show you one or two that cesium time. Time is very important, because that will be good for all.
Sure, sir.
So now you can see that this is how the system at the international level works. All the national laboratories, they contribute for the time measurement through atomic clocks. Okay, these atomic clock or cesium atomic clock. And through that, we get the Indian Standard Time. In India, we call it Indian Standard Time, which is basically coordinated universal time plus 530 hours. And these are measured with different accuracies or uncertainty, we call it. This is 1 second, we use telephone lines and other things. These are network lines like in your mobile systems and other. These are ISRO, which are doing the precise time. Dr. Nitendra will talk much on that. Okay. And these are the just a glimpse that these are the cesium clocks which we are using here, and these are the GPS monitoring system, and this is how we transfer to the satellite, through satellite to the ISRO system, and ISRO do their measurement. And now Dr. Nitendra will also talk a little bit more. So I'll just like to give you that synchronization of these satellites are, the clock in these satellites are very important. If you want to get a very precise point, you need minimum 3 satellites. Now from one satellite, you can get 1 arc, from another you can get crossing arc, on third you get precise value can come. So this accuracy is very, very important here. The satellite synchronization, if it is 100 nanosecond, it gives positioning of 30 meters. So NPL has improved up to 2.8 nanosecond at international level. We are the 4th in the world to have this type of measurements where we can measure up to 2.8, and we have given ISRO the measurements. ISRO is taking traceability from us, and from there they are giving their to these satellite. They are synchronizing that through the traceability of NPL, and that's why they have a better measurement system. Okay, so at this point, I thank you all for this. This is concept of measurement. Little bit I have talked of. Maybe in the series of other seminars, we can talk more on these things where we can precisely define, say, time in more detail, all other 7 base unit in more detail, and all this. Thank you very much for giving me this opportunity. I really enjoyed it. I hope I was able to convey what little bit I have the understanding of this subject. Thank you.
Definitely. It was great to have you, sir. So now I think we can have Nitendra, sir, now. You can continue the session.
If anyone has any questions, you can write them in the chat box.
Hi, sir. So we will resume from the question that we left on because of the network issues. So what is NavIC and how does it function?
Yeah, so I'll continue the same thing. So NavIC, as I was mentioning, it's a constellation of satellites which is known as Indian Regional Navigation Satellite System, which consists of so far 8 satellites, out of which 7 are dedicated for the public domain and 1 is still restricted to specific utilization or strategic purposes. So basically how it functions, as Dr. Ojha was mentioning, you need minimum 3 satellites to cover this 360 degree of area, like, everything is circular measurement. So you cover 120 degree each by that. So more the satellites, more precise you have the measurement or uncertainty or accuracy. And presently our NavIC is one of the most precise system or most accurate positioning system with an accuracy of around 10 meters on land and around 20 meters in sea area or oceans. So basically this is how it is. So NavIC is more about having a constellation, its own country's own positioning system. And why it is important to have our own system, why it is necessary to have its own system is also very peculiar to understand. So I'll go back in time a bit. In 1999, when the Kargil was there, at that time we were utilizing the GPS, the Global Positioning System from US, for all these type of mapping and navigation. So at that time, to locate the location of the around the warfare area, so we asked the US government to give us the data, and they denied it. And because of which the war elongated for a longer duration of time, because it's like, you are fighting in a dark with a blindness. You cannot see what is happening around. So to have that sort of independency, it is very important to have your own system, so you don't have to rely on someone else. So in 2012, in fact, in 2013, first satellite was sent under this entire strategy, and that's how you develop your own network. So far, as I mentioned, so far we have 8 satellites, but it will continue up till as a recent target up to 24 satellites. And so far we are saying IRNSS or NavIC in this region, but this will contribute to a bigger picture, which is known as GINS, the Global Indian Navigation System, which will be like a GPS. So far we are navigating, or we have the access to Indian continent and plus 1500 kilometers surrounding of the borders. That area we are mapping with this. But once this all satellites will be there, we'll be able to cover the entire globe for our all positioning system applications.
Thank you, sir. You actually answered one of our questions we were going to ask. So the next question, I will hand it over to Ritika. She can go ahead. Ritika, you're on mute.
Hello, sir.
Hi, Ritika.
So I just wanted to know that, like, do we Indians have our own? Do we have our own GPS?
Yeah, so basically NavIC is basically our own GPS, if you say. So when we use the term GPS, GPS is basically short for acronym for Global Positioning System, which is the United States system, the positioning system. But India is having this NavIC is basically Indian positioning system, or you can vaguely say it's Indian GPS. Because you can say vaguely stuff, but why do you need, like, you need it for navigation, which is one. Of course you need, if you want to have a traffic system management or vehicle tracking management, or navigation. Apart from navigation, you can use it for disaster management. Like you can have the mapping of area where you can visualize what is about to happen or what is happening, then where to locate stuff. So that sort of applications are there, and that's why you need your own positioning system basically. So that is why India is having its own positioning system, which is NavIC, and it has now been, for example, in 2019 April, if I remember correctly, the government of India asked all the commercial vehicle manufacturers to put the tracking device in all commercial vehicles based on NavIC. So, even in, for example, if you have if you want to supply some say grain from one place to another using the trucks, which is a commercial vehicle, for example, and something happened in between. So you can have a tracking system and you can track precisely where it is, what happened to it. So like this is one example. You can utilize so many applications of in this manner. So it's a part of system, and it's becoming the part of system now. Like in 2020, most of the new phones which are coming in India, they have this. Earlier, the phones had only GPS or GLONASS to be. If you have read the specification, the compatible to GPS, GLONASS, and stuff. Now they have compatibility to NavIC as well.
Like, sir, I am really satisfied with what you explained, but then, like, is this NavIC app really better than the GPS till now we use?
Before answering this question, you need to understand that NavIC is not an app. This is very much to understand. Like, as we say, GPS is not an app. Your app is like your maps. Maps are your app. Like you can use a TomTom, you can use Google Map, or you can use any other mapping system. They are your app. But when they track you, or when they track the vehicle or something, they use the data which they are receiving from this positioning system. So, for example, consider you are using Google Map. Everyone use Google Map, for example. So you are using Google Map. Google Map can take data from GPS. It can take data from NavIC. It can take data from GLONASS. It can take data from Galileo, which is from European Union. It can take data from Baidu, because so far we have these 5 positioning systems. So the accuracy of your tracking or accuracy of your route will depend on the accuracy of this data, basically. Okay, so when for example, I give you a practical example. When you drive using Google Map in France, for example, it will show you that there is a camera, there is a red light, there is a camera, there will be a policeman standing ahead, so just drive safely. But when you're driving with the same map in India, it will show you, okay, there are highway here, there are major road, but it may not show, like, the small trails around, or the camera around, because it depends on accuracy. However, if you use the NavIC as the positioning data, the NavIC is very much advanced and accurate from all others. So then you will receive all this precise information as well. So that's how it is. So in terms of app, you can use any app you want, but to have the accuracy or better measurement, as Ojha sir was saying, better measurement comes with better data. So NavIC is having one of the most advanced data. So as I was mentioning, the accuracy is within 10-meter range. And while GPS has an accuracy of 20 to 30 meter of range. So, you will have better guiding and better tracking using the NavIC system.
Thank you so much, sir.
Now you will be more convinced utilizing NavIC.
Yeah, now like I've understood the difference between like Google Maps or like any other apps and NavIC. So,
Right.
which brings me to the next question. So as you know, Google Earth, how do you think is like, does India have its own system like Google Earth?
Yeah, so as I was mentioning in the previous question, everything depends on data. So you are receiving the data from satellites and everything. Now it depends on you, how you represent it. So the one example was this: you can represent it using Google Map or whatever system for your practical situation. You can also use it data for mapping the Google Earth as Google Earth is there. India also has its own system, which is known as Bhuvan. So I'll go a bit in the history. So when India decided to have its own positioning system, the old navigation satellite and constellation system, or remote sensing system, you can call it. There are various applications. So at ISRO, Indian Space Research Organization in Bangalore, they set up so many other divisions specifically for this purpose. And there they came up with the system named as Bhuvan. So Bhuvan is basically, I utilize Bhuvan a lot. I would say more than Google Earth, because it has amazing capabilities. I'll tell you briefly what they are. So Bhuvan is exactly, or I would say more advanced version of Google Earth. It has both the mode, 2D mode of representation and 3D mode. Like you can watch it as a map, or you can also map it as an Earth in 3D. And when you go to this Bhuvan website, there is a dedicated portal of it. You go to that, and there you can map all sort of data. For example, the distances, the area. For example, if you want to see how much the area there covered by the forest in some region, or where there are physical water bodies in some regions, all that information you can retrieve from there. Or if you want to see, for example, if you want to like figure out what will be the terrain or that sort of thing between 2 point or two distances, everything you can retrieve from there. It is very advanced, and it is, as I mentioned, it is more accurate than Google Earth. So try it once, and it's amazing.
Thank you, sir, for your wonderful insights on the topic. And that was the last question. That was our last question. So thank you so much for like entertaining our questions.
My pleasure.
We would like to thank the speakers, Dr. Ojha and Dr. Nitendra. We are so delighted that you could be here with us today. It was an amazing and interesting session. We learned many new things about the new measurement system and NavIC. We're looking forward to more such sessions in the future.
We would also like to thank the audience for joining us for this event and the organizers for making this event successful. Thank you.
For the last thing, we would like to invite Neelo ma'am for a vote of thanks.
Thank you so much, Sana, and all students. Thank you for the most wonderful session, Dr. Ojha and Dr. Nitendra. It was indeed enlightening. And how did you find our questions? I'm sure they were as interesting for you to answer as for the children to pose them to you. And thanks a lot for sharing your knowledge, your insights, your expertise, and solving so many mysteries that may have been there in the young mind. And I'm sure now, equipped with your answers, they would love to delve even more deeply into these concepts. Uh, Thank you to the moderators for carrying the session so smoothly, to all our viewers, students, teachers, and leaders from across campus who may have been present with us through the session. Thank you to Rahul and Samyak. I hope I have the names correctly. And thank you to them for the IT support. Thank you also to Ms. Vinita Sharath, our STEAM coordinator, and her fabulous team for curating this session for us. Thank you so much. Have a wonderful day ahead.
Thank you to you too. Have a nice evening. Enjoy the festival and the new year.
Thank you. Same to you from all of us. Thank you, Dr. Ojha.
Thank you. Thank you. Thank you to all. It was really nice and enjoyed all the questions. Thank you very much.
Thank you so much. So with this, we'll end the session. Thank you everyone for joining.
Thank you.
Thank you, Rahul. Thank you so much.